Here's another example of using the reduction of order formula. Our differential equation is x squared y double prime minus 3xy prime plus 5y equals 0. We're given that y1 equals x squared cosine of natural log of x is a solution. We see that our equation is not in standard form. Putting it into standard form gives us y double prime minus 3 over x y prime plus 5 over x squared y is equal to 0. At this point, or maybe previously, the question might come up, whatever happens with 5 over x squared y? Like, we never deal with q in the formula or in the process. Well, I guess it shows up in the process, but we never deal with q in the formula. The answer is, as will be evident throughout the rest of this chapter, q is built into how we got y1. Generally speaking, you're not going to be starting with a known solution. This process gives us a second solution and is useful for a theoretical concept that's going to show up later in the chapter. At this point, though, we're going to say we've got that p of x is equal to negative 3 over x. So e to the negative integral p of x dx is e to the positive 3 over x dx. I'm going to go through this because it's something that people flub a lot. The 3 is a constant. The integral becomes natural log of x. So this is e to the 3 times the natural log of x. That 3 becomes an exponent on x. Some people put it in funky places. So this is e to the natural log of x cubed, which just becomes x cubed. y2 is equal to, if you refer to the formula, y1, so x squared times the cosine of the natural log of x, times the integral of e to the natural log of x cubed, well, that's just x cubed, divided by y1 squared, and so x to the fourth times the cosine squared of the natural log of x dx. That's going to give us y2 is equal to this x squared cosine of natural log of x times the integral of 1 over x times the secant squared of the natural log of x dx. You can see we're going to integrate this using the substitution rule. The substitution is u is equal to the natural log of x, and so du is equal to 1 over x dx. That gives us y2 is equal to x squared times the cosine of the natural log of x times the tangent of the natural log of x. You can see that the cosines divide out. y2 is then x squared times the sine of the natural log of x. Now that you've seen both the process and the formula, you may wonder, we have this formula. Why would we use this process? A couple of reasons. Number one, you might be asked to use this process on an exam. Number two, when we have a non-homogeneous differential equation, right now the only way we can handle this using reduction of order is to use the process. That'll change by the end of this chapter, but it's where it stands now. So here's my recommendation. For homogeneous differential equations, use the process, not the formula. This time our equation is y double prime minus 4y prime plus 3y equals x. And we're given the solution y1 equals e to the x. All right, we're going to start with y2 equals u times y1. Spoiler alert, we're going to find out with a non-homogeneous differential equation, this is kind of a lie. It's actually the case that u times y1 is going to be cy2 plus yp. The reason for that will be apparent as this unfolds. For now, right now, we're just going to say y2 equals u y1. Since y1 is equal to e to the x, we have that y2 is equal to u e to the x. And you can confirm that y2 prime is going to be u prime e to the x plus u e to the x. And y2 double prime is going to be u double prime e to the x plus 2u prime e to the x, because we collect like terms, plus u e to the x. Now, substituting that into the differential equation that we have is going to give us u double prime e to the x plus 2u prime e to the x plus u e to the x. Are you tired of hearing e to the x yet? Minus 4y prime. So minus, don't forget to distribute that negative 4. 4u prime e to the x minus 4u e to the x. And then plus 3y is going to give us plus 3u e to the x equals x. You'll note every term that has an undifferentiated u is going to add up to 0. You can see why in the first video of this series. And for what we have left, we're going to end up with u double prime e to the x plus, looks like we have 2u prime minus 4u prime. So actually minus 2u prime e to the x is equal to x. Using our substitution that w is equal to u prime, we get w prime e to the x minus 2w e to the x is equal to x. And if you look at that equation, it's not separable, but it is linear. So we're going to put it into standard form so we can get an integrating factor. W prime minus 2w is equal to x e to the negative x. Integrating factor from the last chapter is mu is equal to e to the negative 2x. And so on the left-hand side, we have the derivative. This is all functions of x. So the derivative is with respect to x of e to the negative 2x times w is equal to x e to the negative 3x because we had to multiply on both sides by mu. We get out of this mess by integrating on both sides with respect to x. The left-hand side pops right out. We got e to the negative 2x times w. The right-hand side requires integration by parts, the result of which you can verify is negative 1/3 x e to the negative 3x minus 1/9 e to the negative 3x plus c. At this moment, you may say, Dr. Matt, you told me before in a previous video, you don't have to worry about any of the constants. You might also note, when I said that was true for a homogeneous equation. Let's keep going with this, and then I'll come back and deal with some caveats. Isolating w is going to give me w is equal to negative 1/3 x e to the negative x minus 1/9 e to the negative x plus c e to the 2x. Remembering that w is equal to u prime, and then integrating using integrating by parts as needed, and then collecting like terms because they're going to show up here. We get the result u is equal to 1/3 x e to the negative x plus 4/9 e to the negative x plus c e to the 2x. Now remember, we originally said that y2 is equal to u times y1. So we might say that y2 is equal to, remember y1 was e to the x, right? That's what made everything so easy to begin with. y2 is equal to 1/3 x plus 4/9 plus c e to the 3x. Now let's take a moment and trace back where all this came from. I know I didn't show you the integration by parts or anything like that, but that's kind of beside the point. At this point right here, we had the derivative with respect to x of the product of e to the negative 2x times w is equal to x e to the negative 3x. Now, why do we have that x e to the negative 3x? If we trace it back, that only exists because the right-hand side of the differential equation was x. In other words, that's there due to the fact that it was a non-homogeneous differential equation. So let's trace this x here, and then x e to the negative x here, and then that integration by parts. And neglecting the constant of integration, that gave us these gnarly terms with the x e to the negative 3x tracing that through again, and then more integration by parts, yada, 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 you can see I'm singling out all the terms that don't have that CE to the x. So the right-hand side has terms 1/3 x plus 4/9 that only exist because the equation was non-homogeneous. What that means is that the particular solution y sub p is that 1/3 x plus 4/9. The part that has the c in it, that term, came from the constant of integration c. Now, if the right-hand side had been 0 to begin with, we would have had that constant of integration anyway, right? So that's the part that always would have been there. The part in orange is due to the fact that it was non-homogeneous to begin with. That part in orange is actually our y2. And remember, when we put this together using the superposition principle, we're going to have a c2y2, so we neglect this constant of integration, and therefore we have that y2 is equal to e to the 3x. And that's actually how this shakes out when it's non-homogeneous. And that's what I meant earlier when I said that uy1 is actually going to be cy2 plus yp. So when we have a non-homogeneous differential equation and we use an integrating factor and then we integrate, we have to remember the constant of integration, and that's the part that's going to give us y2. The part that doesn't have an arbitrary constant, we have to remember all the coefficients and keep all those clean, because that's our particular solution, and that 1/3 and that 4/9 are required for this to be correct.